How do you go from a planar wedge dash diagram for a cyclohexane ring that's got substitutions on the ring to drawing it in a chair form in which the substituent groups are all oriented in the correct direction? You have to do this to be able to calculate strain, steric strain between atoms, if it's 1,6 or 1,7 atom interactions. Okay, so we're going to do that by placing the atoms of this ring structure in the wedge dash diagram on a small part of the diamond lattice. Remember, this is just a scaffold, and we're going to use it as a guide. So first of all, one has to take this structure and actually know that it's also represented by this. In fact, there's a CH2 group here. And an OH, and I've color-coded those red. And that also, as I number the ring, I'm going clockwise around the ring. So I've got to keep the same clockwise orientations when I transfer this to a chair form. These groups are 1, 3 apart in this methyl group compared to this group, the CH2OH group on carbon 1. So now let's transfer to the diamond lattice ring. And notice the cyclohexane ring is red here. I've made a bold chair structure here, and with number 1 carbon highlighted, and we're going to simply transfer the CH2OH group and the CH3 group to it. Okay, let's do it. So here's the CH3 group, because the CH2OH group, because the CH2OH is pointed up, because this is a wedge on carbon 1, we have to point it up on this chair structure as well. So it's in the axial position. So this is going to be connected directly to a C. And then I have to add the H's. Well, I just used the diamond lattice to project the H's in the appropriate direction. So I just follow in this direction. I have a CH, another CH, and then going back I'll have an OH. And you could vary this, but essentially you've got to follow the diamond lattice, because this represents how they're tetrahedrally bonded and oriented on that carbon. So now that's 1. So we have to go clockwise around the ring. So this is carbon 3. So the methyl group is pointing up. So in this case it was in the axial position as well as pointing up. I just left it as a little sphere, and I'll show you how to add the carbon and the hydrogens to that next. So here we are. I've actually just added it as a CH2 and then an H projecting backward, and we're going to see how that's translated into a 1,7 atom interaction. But now I'm going to I have to add bonds to the diamond lattice, because none are there to hang on the hydrogens. So I do that really simply, because if you look at how I'm tracing the cyclohexane chair here, this is the scaffold onto which we place the atoms. This carbon is in this one position here, and I have to add 2 hydrogens to this carbon in this basically up-down orientation of a cyclohexane ring. Well, I simply would have to add 1 axial to it, again assuming the orientation of the ring is this way, and then this bond here would be parallel to the bonds 2 over 1, 2, and 1, 2, and then I simply add the H's to it. Now of course the last H is pointed back, and it's actually overlapping with the H from the CH2OH group, indicating a really strong 1,7 atom interaction. So the diamond lattice is there to show you the orientation of atoms and bonds, and allows you to place them to correctly look at steric strain in the molecule. Finally, one last thing. If one looks at different representations of a substituted cyclohexane ring, there's the chair form, and then there's the wedge dash diagram, in which the ring is represented just as this hexagon. One has to be able to go interchangeably between both of these. Now let's look at this chair form. This X is actually pointed up because there's a hydrogen pointing down here, not shown, and this Y is pointed down because in the equatorial position, because there's a hydrogen going up axially. So again, this is equatorial, but this is up and this is down. So now we translate this into a wedge dash diagram. We have to keep the same orientation around the ring. So we'll call that carbon 1. This is carbon 1. This X is pointed up, so we use a wedge. And then going around the ring in the clockwise direction, we have the next group. It's equatorial, but it's pointed down. So one has to be able to go from here to here, because if given 2 different molecules, either in this form or this form, it's easiest to transfer it to the wedge dash diagram to answer the question, are these molecules identical, are they diastereomers or enantiomers?